Good morning, good afternoon, good evening to all of you. Welcome to the fourth Color Theory webinar in a series of 5, brought to you by Data Color Academy. In the previous webinars, we already talked about color and appearance, how to communicate color, and about color coordinates and color differences. The handouts and the answers to the numerous questions we got can be found in the handout section of this session. For those of you who missed one of the previous sessions or who want to replay it, you will get a link to the page with all the recordings by email. So let's start today's session. Bill Binder, Senior Color Scientist, will tell us more about color tolerances this time. Bill, I hand over to you.
Thank you, Ann. Hello, everybody, and welcome to Color Theory Part 4. Today, we're going to talk about color tolerances. Let's get started. We'll have a quick review. In some of the last sessions, we talked about the colorimetric description, whereas visually we use the light source and the object and a human observer to get a color perception. We also then talked about a colorimetric description, where we actually do this numerically, where we have our illuminant data, we have a reflectance curve, which is the object, and then we have our standard observer functions that give us a colorimetric description. We talked about the standard observer, and this came about from the experiments done in the 1930s and 1964, where we had a human observer match the spectrum colors to give us the human response to color. And those are set up in sets of tables. We have the 1964 10 degree and the 1931 2 degree color matching functions. With those, we generate what's called the tri-stimulus value. And an example here, what that means is really that we can take an object color and we can ask the standard observer how much red, green, or blue imaginary light is required to match that. We also talked about metamerism and the effect of having two curves two samples that will match under one set of conditions but will mismatch under another set of conditions. We talked about the spectral curves crossing at 3 or more points in the spectrum. Last week we started to talk about CLAB, and again, 3 dimensions of color. We described the hue, chroma, and lightness, and how CLAB color space actually follows this very, very closely, where we have the hue going around in a circle here, the different colors. The CLAB is an opponent color system where we have a yellow, blue, red, green setup. We have the lightness going from dark to light in the center. It's in different shades of gray. Also, we talked about in CLAB, here's another view of CLAB color space, where the key is the lightness, the shades of gray. And then when you pick any hue, as you come out, you increase in saturation. And this is the hue. And as you change, coming around in a circle, you change in different hues. We also talked about color difference. And here was a specification that I had given of a color difference calculation, where I was comparing my red apple I had my red apple 1 and red apple 2. And what we did is we measured the apple. We have the spectral curve. And what we've done under 3 illuminants, we've calculated the XYZ values. So basically, that's like we showed the standard observer the apple and asked for the amounts of red, green, and blue light that will match that. And that data is right here under the 3 illuminants. We then calculated the L, A, B, C, and H values, the CLAB values for that. And those are right here for the standard. And then we did the same thing when we measured red apple 2, or the batch in this case. So we again got the XYZ values, and we got the LAB values here. And then we're going to do the color difference, which is going to be the difference between these two. And shown below here is the color difference. For example, under D65 10 degree, my apple is positive 3.69 in lightness. That means it's lighter than the standard. The DA is minus 3.92. It's in the negative, so that means it's greener, or in this case, we would say less red. And the DB, the yellow-blue, positive indicates it's yellower or less blue. The DC, which is the difference in saturation, is minus, so it's less saturated than the standard. The delta H is the hue difference. It's 1.93 away from the hue line. And the total delta E between the two is 5.44. And quickly over here, you can see where here's my batch, and my standard is positioned here in the AB space, and this is the lightness direction. You can see that the batch is lighter, it's higher from the delta L, and you can see that it is less saturated. The standard is here, and the center, the gray of the space is here, so it's less saturated, and it's off the hue line by this much. This is the sort of the delta H calculation here. And I'm also showing here an example of the color of the two and their reflectance. But this is a sort of a nice complete color difference, or an analysis of those two colors. One thing I want to do is do an update. Last week I also discussed the CLAB polar coordinates and the calculation of delta H. And the diagram I used was not up to the current one, so I wanted to update just to show you the calculation of delta cap H, or DH here. Here's the equation for DH calculation, and how it's done is really we have it's using the C star values. So this is the C star of the batch, and this is the C star of the standard. And what we're going to do is we're going to calculate what's called the geometric mean of these two C stars. And that position is going to be right where I have this black star. And that's based on the calculation of C star of the standard times C star of the batch and the square root of that. So that sets this geometric mean here. And we're also then, we're going to, the delta H is the hue angle between the two. And basically the equation uses the DH divided by 2. So it uses this angle here, and we draw this other vector in here. So based on that, we now have this angle here. We know this DH divided by 2. And then based on using the sine function, we're going to calculate this distance over here because we set up the right triangle here. So we know the hypotenuse of this line, which is the geometric mean, and we know the angle, so we can calculate the opposite side. And that'll be 1/2 of the DH value. And then since we multiply by 2 here, we define as the distance between the stars here is the DH, or capital H. That's how the calculation is made. You don't have to worry about how this is calculated or anything. In use, you're just going to know that the DH is the distance in space, sort of between the on the hue line. And we'll talk about this more in detail. But I just wanted to update this to make sure that everybody sees how this is calculated. Okay, let's start off today. Today, color tolerances. When we talk about color tolerances, we're really talking about acceptability versus perceptibility. Now, perceptibility defines a just noticeable difference between a standard and a batch. That means we can see a difference. It can be very small, and the human eye is very good at picking up small color differences. Whereas acceptability is the largest acceptable difference between a standard and a batch. And a definition of color tolerances are the colorimetric limits that define when a product is acceptable. Realistic tolerances are usually based on the maximum acceptable color difference rather than on a minimal perceptible difference. And that's an important point. It's a good tolerance should be based on what's the maximum acceptable limit, rather than just a small limit that based on something that you can see a difference on. A color difference is the amount of color difference or variation that is commercially acceptable. Again, a key statement. What is commercially acceptable? A lot of times we use the term a commercial match, or it's a good enough commercial match. You have to come up with that number between a supplier and a vendor. Color tolerances will vary across industries. A good tolerance represents a compromise between the capability of the process and the customer's requirements. Again, the key term here is a compromise between the process and the requirements. It doesn't pay to create tolerances that are so tight that you can't meet them, or that it really costs a lot. So you have to look at the process and make an analysis of the situation. Okay, a lot of times, let's start out with a simple tolerance would be a delta E tolerance. And if we use a delta E tolerance, really what that defines as a sphere in the C-Lab color space. An example here, I'm showing DE of 1. Again, I'm showing you this is the 2D representation over here. This is the AB plane, and the lightness is always usually shown on the right here. This actually is coming out at you from perpendicular from the page. And you'll see that this is a circle right here of DE of 1. And over here we have 1. And over here I just have a 3D representation, and you see it's a sphere. And in this case, the batch happens to be outside. It's lighter, it's outside the tolerance, and you can see that up here. We can also, with DE, we can just define a simple box tolerance. We can have DL, DA, DB, and a tolerance of 1 would define a box in color space. So I have DA plus and minus 1, DB plus and minus 1, same thing with L, and that would create a square box in color space. Here's where I'm taking the box and making it more into a rectangular box, where I have the hue or the delta A I've made plus or minus 0.5. I stretched the delta B, and again, when I'm visually over here in 3D, you're creating this rectangular box. Okay, how do we determine tolerances? One way is from historical batch data. You can get measured colors and see what where the samples fall, and you can say whether it's a pass or a fail. So here I have a standard measured, and I have a bunch of batches measured, and this is just in the AB plane. We're forgetting about the lightness for now. But what we can do is, one thing we can do is we can visually assess them. And in this case, I'm showing the samples that are in green, I've said are pass or they're acceptable, and the samples in red, I'm calling a fail or unacceptable. So now the goal would be, how do I create a tolerance for this? Well, one way with a DE tolerance, which is going to be the spherical tolerance, or in this AB plane, a circle, I'm going to try and get this circle around the pass samples and exclude the fail samples. But as you can see, with a situation like this, it's not that easy. I can get around some, but not all of them. So if we take another look at a different case here, if we're going to use rectangular delta L, delta A, delta B, in the AB system, again, I could get around some, but not really all of the samples. I don't have the capability to get around all these samples. Take another look. Now here I'm trying to use a hue angle with a delta C, and now I'm starting to get a little better. I have some chances now of getting the samples to the acceptable ones inside here, but it's still not complete. Here I'm using a rectangular LCH, capital LCH, and in this box I'm getting a lot closer, but I still have some areas that I can't cover. So finally we get to this situation. I find that I can do this with an ellipse, or in three dimensions it would be an ellipsoid. So I can now include the acceptable batches and exclude the unacceptable ones. So an elliptical tolerance based on DH and DC can include the acceptable and exclude the unacceptable one. Okay, that gets us into ellipsoidal tolerancing, and we'll start talking about CMC, color difference equation. And as you see over here, this is again the sphere, and DE as being the radius of this circle or this sphere. An ellipsoid is we're stretching out this sphere, and the equation of an ellipsoid is shown down here. And the key points on this is that the denominator here, the ABC, those are the semi-axes of the ellipsoid. So in other words, you see here A, B, and C are these terms down here of the semi-axis. The equation, the XYZ, defines this surface, the surface of this ellipsoid. Now in CMC and a lot of other ellipsoidal equations, what is done is we're using this same equation here. So if we look up here, we have the SL, SC, and SH. First of all, what CMC does, based on the color that the standard, CMC will calculate internally these tolerances, the SL, the SC, and the SH. It will calculate that. So in other words, what it's doing down here, it's calculating the semi-axes of the ellipsoid. And that's for every color. You go to a blue, you'll have a certain shape. You go to a green, it'll calculate some different other color, other shape. So those are the tolerances, and those are in the denominator here. You can see the SL, SC, and SH. The color difference is up here, the delta L, delta C, and delta H. That's what you calculate from when you do the standard and the batch calculation. So those are plugged in up here, and then the equation is set to calculate the delta E. Again, here I'm just showing you a little more detail. Again, showing you the ellipsoid with the SH and SC, the semi-axes, and here I'm showing you where a batch might be plotted, and there's a delta C and a delta H might be plotted here. And if we're looking at it from the SL, from the lightness direction, I'm showing you again, the batch could be in here. There would be a delta H and a delta L plotted. The key though, how we're using this is, and here's an example for, again, this is CMC. And when I set up a CMC equation, I have set up a tolerance here. I'm showing you a tolerance in our software where I can set up a DE tolerance. And I also have control of the L and C, which are these adjustment factors. CMC gives you the opportunity to adjust these. In other words, the SL, SC, and SH are going to be calculated by CMC based on the color of the standard. But by adjusting these LCs, or you can make an adjustment. Now, last week I actually showed an example where I did adjust to C just to show how it looked, but technically you don't really want to do that. There's some mathematical quirks that normally the C in CMC isn't adjusted. Normally the L is adjusted. So L is the lightness factor, which allows adjustment of the DL semi-axis. Now, what does this really mean? So when if you get a DE CMC of 1, that really tells you that the batch that you've measured is on the surface of the ellipsoid. It's right in between possibly a pass and a fail. Be a situation where you might want to visualize it and it might say check or something. If the DE CMC is less than 1, that means the batch is inside the ellipsoid. So it would probably be the pass situation. And if the DE CMC that you calculate is greater than 1, that means the batch is outside the ellipsoid. So basically, this equation is run all the time to come up with your delta E, and that's going to be based on here. Now, if you want to change the delta E, it's called a commercial factor. If you want to make it tighter, you can put, let's say, a 0.5 in here, which would shrink the ellipsoid in all of it on all dimensions and make it smaller. So then 0.5 would indicate the surface of the ellipsoid, and that would be your pass-fail criteria. Okay, here's an example now of CMC where I'm changing the L, the small L adjustment factor. Normally CMC 1.1 is used a lot of times in the paint or plastics, whereas CMC 2.1 is used in textile. But here's a 3D representation of the CMC ellipsoid with 1.1. And notice when I changed the adjustment factor to 2, the ellipsoid was stretched in the L direction. So I'm going to include in past samples that are lighter and darker. And again, in textile, looking at textile fabrics a lot, a lightness difference isn't visually as bad as in possibly some other industries. So that's the factor that usually changes. And whenever you reference CMC, you'll see it says CMC 2:1. That means you're using this factor, or a lot of times you'll see 1.1. But you should sort of reference to know what the adjustment factor is when you use CMC. Okay, CIE 2000. Talked about this a little bit last week. Again, CIE 2000, a color difference equation based on the CLAB color space, similar in a sense to the CMC because it's an ellipsoidal color space or color equation. And in this case, the equation is up here, and you can see that we have this SL, SC, and SH. This is similar to CMC, where where CIE 2000 is calculating the semi-axes of the ellipsoid for you. And CIE 2000 was supposed to improve gray colors. There's an improved performance for blue colors, uses a rotational factor over here. You have control again in this equation of the DE as a tolerance. You also have control of the LCH factors, the KL, KC, and KH. So basically, as you change this, you will skew the ellipsoid in a certain direction. For example, if you put a 2 in the L, you'll stretch it like I showed before in the CMC. I don't have a lot of experience using this in different areas, so I'm assuming you can change these and stretch these around. But right out of the box, CIE 2000 is trying to give you a DE that is the representative of a visual acceptability. Again, same thing with the number. DE of 1 means you're on the surface of the ellipsoid. Less than 1, you're inside, would be a pass. And if your DE is greater than 1, you're on the outside. Okay, I just want to talk quickly about something we call AI pass-fail, which is computer-generated tolerance based on visual acceptability. If you want to take the time for individual standards, you can base a tolerance just on that standard. And basically, with this AI approach, you can mark each batch as either a pass or a fail, and the program will try to create an ellipsoid that includes the pass samples and excludes the fail samples. You'll have your low and high LCH parameters, which will set up the semi-axes. You can offset the actual ellipsoid can actually offset from the standard if it needs to be, and it'll set up a pass-fail. The system, based on the samples that you use, will create these for you. In this example, these are just numbers that I've had in there. But here's an example of an ellipsoid that was created this way, and I'll show you a few examples. Here's a light gray sample that was created with the AI approach, and you can see that this is the ellipsoid that was generated. Now here's another color. This is a yellow gold. Notice that in this case, the acceptability is more towards the red side than it is towards the yellow, and it's definitely in plus saturation here, as you can see the hue line moving along here. Here's a 3D representation of that color. Here's an orange sample. Again, this is the hue line and showing you what it looks like. And this is a 3D representation. And here's a green sample. And this approach is good if you have historical samples. You also should have pass and fail samples because it'll take into account both. In this case, you notice over here, the hue difference is it cuts down on the yellow, but there's not a lot of fail samples over here, so it's just assuming that these will be passed. So the fail samples are good, as you can see over here. The fail samples help define the ellipsoid. Okay, what I want to do here was just to quick go into our tools here, the software, and just to show you a few things. We had talked about, I have a sample here, just a sample, a standard and a batch. And in this case, the standard and batch is, the standard and batch, you can notice, first of all, that these two curves are not metameric. They're not crossing and everything, so these two curves can come together. But if we look at the color differences up here, first of all, I have the standard, I have my XYZ, I have my LABs, and for my batch, I again have my XYZs, my LABs, and this is the way I like to run. And I'm just showing the color differences. I'm showing CLAB DE, I'm showing the CMC, I'm showing the CIE 2000, I have a metamerase index, and I also have a CMC pass-fail determination. And for example, in this color, if we take a look at, I'm going to switch to CMC. Notice how this is the CMC representation of this. Let me make auto scale here. And in CMC, you can notice where the batch falls. It falls inside the ellipsoid. And so it's a pass. And if you look at my CMC DE, it's 0.9. So it's 0.9, so it's under 1, so it's inside the ellipsoid. We take a quick look. I can show you here's a 3D representation, and you can see this is the ellipsoid, and the batch is inside that ellipsoid. Come out here. And one of the things I can change here, for example, let's say I wanted to change that tolerance. I'm going to go up and edit my CMC tolerance. And let's just go in here and instead of small l, the adjustment factor of 2, let's go back and make it 1. So if I change that to 1 and come out, notice that the L has dropped down. So in other words, now my batch is outside my lightness. If I look up here, my CMC pass fail has now said fail, and my CMC DE is 1.71. So I'm outside of the ellipsoid now. And if we want to take a 3D look here, we can see what happened. The ellipsoid is now not stretched anymore. The batch is now up here outside the tolerance. So that's just a way of looking at the tolerances. CMC, you're just going to probably try and use one tolerance and let the ellipsoid be created for you based on the color. Same thing with CIE 2000. If you want to create your own tolerances, you can use software to create box tolerances, or you can create your own elliptical or ellipsoidal tolerances. Okay, let's go back. And okay, that completes the main part of the webinar. I'd like to go over some of the questions from last week that we can go over right now. There were questions on CMC versus CIE 2000. Along the lines of some of these I'll answer together. There was like questions are the differences between them worth changing? That's a tough question. In most cases, I don't think that the differences between CMC and CIE 2000 are that great that you would just automatically switch because of it. I would say that it's basically more of what maybe what your suppliers or what you're actually using in the field. However, CIE 2000 is the recommended acceptability equation at this point. I would say you want to take a look at it, and the trend would be towards using it. Are there negatives where CIE 2000 isn't as good? I don't really have a lot of experience in that area. I'm sure you might find a color here or there that's different, but I don't think there would be a reason to use one over the other. The same question was, what if a mill is using CMC and a retailer is using CIE 2000? Well, that's a little tougher. That's not an ideal situation if two people are using a different one, especially with a tolerance. I think in that case you have to decide. For example, if your supplier is using CIE 2000, or the people you're selling your product to, you might want to use that. And there's no real problem. Both CMC and CIE 2000 are based on CLAB. Color space as its baseline, so it's not like you're going away from anything. You're still in CLAB space. Other question was, with all the different DEs, there's CLAB, CMC. We didn't talk about, there's a CIE 94, which was like an interim before CIE 2000. There's a new equation called DIN 99 from the German standard. DIN 99 actually has its own color space with it. The question of what to use, I think at this point, I would say you want to understand CLAB, you want to know CLAB. You can move to CMC or CIE 2000 without any problem, but I think CLAB is the basis, and if you understand CLAB, I think you're going to be in good shape. There was a question about if the spectrophotometer uses D65 light source, does the illuminant for LEB need to be specified? Well, the question is yes. The light source in the spectrophotometer is really independent of the LEB calculation. The spectrophotometer light source, and we'll talk about that next week, can be anything really. It can be a xenon flash, it could be a tungsten, it could even be a candle for all that matter, because the actual percent R is a ratio measurement. It's a ratio compared to a white standard. So the actual light source doesn't really matter as far as the illuminant for the LAB. However, the light source of a spectral matters in cases of ultraviolet. If you need UV light, if you're looking for fluorescence and things like that, the light source is important from that aspect. But an LAB always needs to have the illuminant and observer specified for it. There was a question on cases where DE is very close but the samples are visually far apart. And there was a question of cases where the DE is very large but the samples look good. In this case, it's kind of the difficult. What you want to do is, in this case, you want to analyze. You always want to analyze your situation. Look at the delta C, delta H, and delta L. Is there a hue difference going on? Maybe the hue difference is large compared to the DE. For example, let's say you have a DE of 3 and your delta H is 0.1. Your hue is right on, but your DE is 3 and your saturation might be like 2.9 or something like that. In that case, the sample may look visually very good, but it's going to have a DE of 3. And that's because the difference in hue is very small. Or you may have an example where the DE is 3, but the delta H or the hue is 2.9, where it may in that case the hue is off and it may look bad, but the delta E is still at that number. So again, always look at the numbers and try and always look at the hue, chroma, and value. That'll always help you. Now, other reasons. Well, you can have gloss differences. You can have a high gloss versus a low gloss. The standard could be high gloss, the batch could be low. And again, depending on the type of instrumentation, if you're using a spectrophotometer, a sphere with specular component included, you might see from measuring a high gloss and a low gloss, you might see a low DE because the instrument includes the specular, and we'll see the high gloss one and the low gloss one being very close, but visually it will look pretty far apart. So always look at the gloss differences between, and we'll talk about that in a little more detail in next week's seminar. Also, any type of difference in surface. If you're comparing a textile to a paint sample, the appearance differences, dissimilar nature of the structure of the surfaces, anything like that. So you always want to try and investigate why you're not seeing the same as you're measuring. And also there could be measurement errors, just the structure of what you measured. You might have been measuring something that was rounded and you got an error in measurement. DEs to different materials, any limitations? Generally not, but you, like we just explained, you could be measuring dissimilar materials that are going to affect the measurements. So in other words, if you're measuring velvet or a velour or something that has a light trap effect and you're comparing it to a solid object or panel, the geometry and the appearance of the structure of the sample could play into the numerical readings versus the visual readings. So you always want to try and to agree. You want to try and find out why is there a disagreement in the difference in the numbers. Okay, there was a question on color difference most accurate for color matching. Now for color matching, whether you use CIE 2000 or CMC isn't really that important. And the reason is that the color matching algorithm basically what it really tries to do is it tries to minimize the color under, and it can just use regular DE. It doesn't need to use an acceptability tolerance like a CIE 2000, because what it's going to try and do, it's really going to try and calculate and minimize the difference under multiple illuminants. So the important thing in a color match, it's going to look at maybe D65, illuminant A, maybe fluorescent. It's going to try to take the formula and adjust it to get the best match under 3 illuminants. You may even look at a curve fit, depending on the algorithm. It might try and get the spectral curves to be as close as possible. So the color matching algorithm is really trying to eliminate or reduce metamerism. That's the real point there. The actual color equation really is not important, and that's more for your case. So whether you just use CLab and you ask for a DE of 0, or whether you used CMC, it doesn't really matter in that case. Another question on that was explain metamerism in architectural coatings. And really, I think in its general terms of metamerism, in any situation, what you're trying to do is reduce metamerism or eliminate it. So in any situation where you create a color, a new formula, you have to be careful. So if I'm in a building and I have a paint and I'm going to try and match it, you have to be careful because metamerism is going to come into play. Even if you go out and you buy a paint in a store and you come home and you paint your house, half your house, and you run out of paint, when you go back to the store, probably what you want to do is get the same paint from the same store so you get the same formula. However, if you went back and just matched the color, the store would match it again, there's a possibility that they would come up with a different formula based on possibly a different spectral arrangement, and you could be in trouble. So metamerism occurs all the time, and it's really based on when you're doing color matching or creating a new formula from scratch. DE calculated by delta L, delta A, delta B is the same as delta L, delta C, delta H? Yes. There was also a question on the vector direction in color space. I think that referred to the hue line, or the line, it's also called the chroma line. I call it the hue line. It's the line from the center of the C-lab out from where the standard or batch is on. That's very important. And in fact, what I can quickly do here is, I forgot to do this. Let me just go back into here. This is in tools again. Notice that this color here, look at the DH up here. The DH is near 0 and the DE is 2. This batch is on the hue line. This is the hue line of the standard. The standard is represented in the center here. The gray of the C-lab space is over here. So in this case, the hue is on. So a lot of times, if you have to correct the color, and a lot of times if you can bring the hue on, you don't necessarily always have to maybe get directly to where DE is 0. And this really applies in cases in formulation or in correction or in production. Getting the hue closer is key. So that's why this vector is important, and that's why the DH is one of the most important aspects. So you have DH, DC, and you can see here in this case, the lightness is really the farthest out, but the hue is on, and visually this color may not be that bad. So I just wanted to cover back that. Okay, we also had a question about dullness and brightness. I'll answer that one later, because dull and bright, those are just terms we use for the lighter, darkness, or for chroma. Like if something is stronger or weaker, the terms that are actually used vary in C-lab. So if you want to say something's lighter, brighter, duller, those are all terms that can be part. It could be saturation, it could be lightness, it could be a combination of two. So that's a little more difficult. Okay, I think that's where we are here. Okay, let's go, and I think that's all I had for today. The next session, we're going to talk about visual and instrumental evaluations. We'll talk about instrument geometry, the different geometries, specular included, excluded. We'll talk about 45 zeros, visual evaluations, light boosts, and I'll try and do a follow-up questions on a lot of the questions that we get, and try and tie everything together. So that's it for today. Anne, on?
Yes, I'm looking at some questions. We'll see.
Okay.
Well, we take a few minutes and then we can deal with the rest later on our next session. I have somebody who says, hello, Bill, we make textile products. Assuming the tolerance is 1, when 2 batches are opposite in sphere, the actual color differences are huge. So should we reset a tighter DE CMC tolerance value, for example, 0.8 for batch to batch deviation?
Again, you were saying that we're huge because of what, An? Could you repeat that part?
They were opposite in sphere, so that the actual color differences are huge.
If the
guess
color,
they are opposites on one of the three axes. I
okay,
think
okay.
that's what you
If the
meant to
color,
say.
differences are that, I think what you want to do is you really want to find, is there a reason? Are you, for example, if it's a textile, are you measuring, is the standard and batch both the same material? Is it the same structure, the same textile? Um, but yeah, in other words, if there is something that you need to change, I mean, I think you have to change it. But again, I would always try and find out what is the situation there. What am I comparing? Am I comparing the two apples to apples in a certain case? So, and again, on that one, if you can give me more detail and you know, we can try, I can try and answer that in more detail. If you can give me more of an example, you can send that in.
Okay, I have another question on how to determine the tolerance if the customers brings color swatch or chips. However, the actual substrate is more porous or is a different material. How to do then? How to determine tolerances in
Well,
this
again,
situation?
the tolerance is also always going to be dependent on, like I said, if you have the samples visual there, that you have the real samples, you would just measure them and see where they fall, and basically, you know, you would just based on where the LABs are, you could try and base it on that. But if there's, again, something going on, like if there's uh, changes that are going on in the process, or you know, if there is something else going on there, it's hard to come up with a tolerance to compensate for something. For example, let's just say an example. If we know that a process is making something lighter or darker, and that's a real variable. So in other words, if you're a printing press or something, and we know that we our lightness darkness varies from run to run a lot, you would say that the tolerance in delta L has to always be greater. That's something that you could put in there. So if you can look at the data, the samples you have, and you can say that, well, based on what I'm seeing here, the tolerance has to be a certain way. You know, that's something you can do. But again, the tolerance really has to be a balance between what you can actually produce at a reasonable cost, and what your vendor or your supplier or your customer actually will be able to accept. Um, Again, with tolerancing, there's no hard and fast rules on this. It's really something to can you measure it, and can you measure it repeatably, and based on those measurements, can you then set these parameters that you can use for a pass fail. And a lot of times there may be a region, like a check, a visual. Like I said, ellipsoidal tolerancing is like that a lot, where if you're near the edge of the ellipsoid, a lot of times you'll say check, because, you know, if you're 0.99 versus 101, why would you pass or fail on a number of point, you know, that close? So you may also have a visual check at some point. In some cases, you have to be under the number, and that's just the way the customer wants it. So I don't know if that helped, but that's you know, from that perspective. And again, if you have any more detail, you can supply a little more detail that on the question.
Okay, I can see some questions that you have been answering while giving all the explanations. So I think it's about time to call it a wrap. Thank you, everybody, for attending this webinar. As said at the start, we will make the recording available, so you will receive the link in an email. The handout will be available for download on our website, or it will be available also during the next webinar. And our fifth webinar in this series will be held next week, Tuesday, May 19th, same time. And we will address visual and instrumental color evaluation. So thank you very much, and I hope to see you back next week. Bye.
Okay, thank you, everybody. If you have any questions, please send them in. Thank you. Bye-bye.